the organic chemistry stream. YouTube. It's your boy JOSHABRAHAM in it. And the in it sounds pretty cringe, or it sounds pretty it's very how do you say? I mean, I could change it to something you know. It's it's Josh Abraham, yo. Nah, that's so bad. It's it's JOSHABRAHAM. Huh? I think Well, I don't have time to waste. I gotta look into organische Chemie. We're doing the first exercise sheet, and the second one. Okay, that's an important one. Okay. No. My only sunshine, I only had you, and I was lying. You are my sunshine, shine.
Imagine bringing your side project to life.
So for let's just search NMR.
In this video,
I did look into NMR, but we gotta look more into NMR. Plus this, what the hell is this? Do we have a lecture note explaining?
we're gonna focus on
Reaction, bioorganic molecules, reactions, redox, reactions, car. What the hell is car? Nucleophilic addition of carb. Reaction now NMR. I think NMR interpretation. Do we have the content? No. I think I should just look into the second lecture note, the whole thing. I did look into IR spectroscopy. I did got some idea of what it is, but I still didn't learn what I need to, like, I still didn't learn those. What is this? I did not learn those functional groups in form of dips in graph. I did not know exactly which functional group is for which, but I look into those. UVV, IR, IR. After IR, it's mass. Okay. So I didn't look into UVV spectroscopy. UV spectroscopy. Oh yeah, got him. Oh no, the general chemistry tutor is not here. Khan Academy. Don't be in Hindi.
Different molecules can absorb different wavelengths of light, and if a molecule happens to absorb light in the ultraviolet or the visible region of the electromagnetic spectrum, we can find the wavelength or wavelengths of light that are absorbed by that compound by using a UV-Vis spectrophotometer. And essentially what that does is it shines light with a range of wavelengths. So the wavelengths range from approximately 200 nanometers all the way up to 800 nanometers. And so we shine that range of wavelengths of light through a sample of the compound, and you get an absorption spectrum. And so here is an absorption spectrum for this molecule, for 1,3-butadiene. If we look over here, we can see that this molecule absorbs most strongly right about here. And if we drop down, we can see what wavelength of light is absorbed most strongly by the compound. And so we see that's just under 220 nanometers. And it turns out to be 217 nanometers. So we call this lambda max, right? So the wavelength of light absorbed by this molecule is about 217 nanometers. It absorbs in the UV region, therefore butadiene does not have any color, it's colorless. All right, let's look at the dot structure a little bit more carefully here. So we have 4 carbons, and all 4 of these carbons, each one is sp2 hybridized, which means each one of those carbons has a p orbital. So we're talking about 4 p orbitals here, or 4 atomic orbitals. And when you're dealing with molecular orbital theory, 4 atomic orbitals recombine to form 4 molecular orbitals. 2 bonding molecular orbitals and 2 anti-bonding molecular orbitals. So let's go over here and let's look at the 4 molecular orbitals, and we're going to focus in on the left side first. The bonding molecular orbitals are lower in energy than the anti-bonding ones. So this orbital and this orbital, these are our bonding molecular orbitals here. And this one and this one are the anti-bonding molecular orbitals. And you can see energy, right? So energy is increasing, and so the anti-bonding molecular orbitals are higher in energy. Let's look at the dot structure again for butadiene, and let's see how many pi electrons we have, right? So here are 2 pi electrons, and here are 2 pi electrons. So a total of 4 pi electrons. And when you're thinking about molecular orbitals, you can think about electron configurations, right? So we have 4 electrons, and where do we put those electrons? We're going to put them in the lowest energy orbitals first. And we're also going to pair our spins, right? So 4 electrons, we're going to put 2 into this bonding molecular orbital, and we paired our spins, and then 2 into this bonding molecular orbitals. So the 4 pi electrons go into the bonding molecular orbitals when you're talking about the ground state. So here's the ground state, the ground state of butadiene.
Luno Homo.
So next we shine
What the
light
hell?
on butadiene, And the molecule is going to absorb energy from the light. And let's look at that here. So there's a difference in energy, right? There's a difference in energy between the orbitals. And in particular, we're concerned about these two orbitals right here. So there's a difference in energy between these two orbitals. This orbital down here, right, this is occupied by electrons, and it's higher in energy than this orbital. So this is the highest occupied molecular orbital. So highest occupied molecular orbital, or HOMO.
Homo.
This orbital right here,
Oh,
right, is
homo.
unoccupied. The antibonding molecular orbital right now is unoccupied, and it's lower in energy than this antibonding molecular orbital. So this is the lowest unoccupied molecular orbital.
Lumo.
So when you're talking about a molecule absorbing energy, we're concerned about the HOMO, the highest occupied molecular orbital, and the LUMO, the lowest unoccupied molecular orbital. The energy difference between those two orbitals is what we're thinking about. So the molecule absorbs energy, and a pi electron absorbs energy from the light and is promoted to a higher energy level. All right, so let me go ahead and right over here. Now we're talking about the excited state. So we shine light on the molecule. So this is the excited state of butadiene. And these two pi electrons stay there. One of these pi electrons stays here, and one of the pi electrons absorbs the energy from the light and is promoted to a higher energy level. So I'm saying this one right here
Gonna go to the LUMO.
was promoted to a higher energy level. It goes from the HOMO to the LUMO. And it had to absorb a specific amount of energy in order to do that, right? So it had to absorb the right amount of energy in order to make that transition. And we know that energy came from the light. And we also know the energy of a photon of light is equal to h, where h is Planck's constant, times the frequency of light, which is nu. And over here for the absorption spectrum, right, we have everything in wavelengths. So we need to write the energy in terms of a wavelength. And we know that the frequency of light and the wavelength of light are related by the speed of light is equal to the wavelength times the frequency. And so the frequency is equal to the speed of light over the wavelength. And we can take that, so frequency is equal to c over lambda, and plug it into here. So now we have the energy is equal to h times c over lambda. And this is really important, right? So energy and wavelength are inversely proportional to each other. And you can think about one wavelength, right, giving you a specific amount of energy. And so this energy difference, right, this energy difference between the HOMO and the LUMO, right, this corresponds to a wavelength. And if we go over here to the absorption spectrum for butadiene, we're talking about a wavelength of 217 nanometers. And so at first it might be a little bit confusing because it looks like we have a very broad, right? It looks like we have a broad range of wavelengths that are absorbed here. And don't worry about that too much. This just results from the different vibrations and rotations of the molecule, which can change the energy differences slightly. And so we don't see one exact wavelength. We end up seeing this broad band of wavelengths being absorbed here. So what you do is you just look for the one that's absorbed most strongly and think about that as being the wavelength that corresponds to the energy difference between these two orbitals here. So that's how to think about it. All right, let's look at another molecule here. So instead of butadiene, let's look at this molecule. So we have ethanol. All right, so here's our dot structure. And if we look at this molecule, right, we know we have 2 pi electrons here for ethanol. So 2 pi electrons. We know that those electrons are going to go into the bonding molecular orbital. So let me draw a line. Right here on this diagram. So this is our bonding molecular orbital down here. And so we're talking about 2 pi electrons. So let's put in our 2 pi electrons into here. And then let me just go ahead and change colors up here. So this up here is our anti-bonding molecular orbital, which we call pi star. Right? So there's an energy difference between the bonding molecular orbital and the anti-bonding molecular orbital, right? So this is delta E. And we talked about the fact that this corresponds to a certain wavelength of light. And so ethanol can have, when it promotes one of these pi electrons up, right, it can have a pi, we call this a pi to pi star transition, right? So the molecule is going to absorb energy, right? And the energy, let me use a different color here, the energy corresponds to a wavelength of light. So this energy difference between our two orbitals. And it turns out that this pi to pi star transition is approximately 180 nanometers, which is below the range of what you're usually measuring, right? When you're using a UV vis spectrophotometer. All right, but we have another possibility here too. So let me go ahead and highlight a lone pair of electrons here on the oxygen, right? So we have a lone pair, right? So we have non-bonding electrons, right? And non-bonding electrons occupy a non-bonding orbital, which is actually a little bit higher in energy than our bonding molecular orbital. So another possibility, we call this N right here. So this is a non-bonding orbital. So non-bonding orbital here, and we can put some electrons into that orbital, right? So we put those two electrons into the non-bonding orbital, and we can have a different type of transition. So we're still talking about a pi star, right? An anti-bonding molecular orbital right here. We can have a N to pi star transition, right? So we can have an N to pi star transition as well, since we have a carbonyl compound. So we're not just talking about pi electrons here, right? The carbonyl, we can think about a non-bonding electron here. And let's think about this energy difference. So this energy difference is smaller than before, right? So this energy difference is smaller than this energy difference. And so what would happen to the wavelength of light that's absorbed, right? So if we have a smaller energy difference, energy and wavelength are inversely proportional. So this must be a longer wavelength, right? So this absorbs light at a different wavelength, right? So a higher wavelength. And it turns out to be, let me go ahead and change colors here. So this energy transition corresponds to a wavelength of light that's approximately 290 nanometers. And so this N to pi star transition, a smaller difference in energy, I should say, corresponding to a higher wavelength. This is an important concept. So as you decrease the energy difference between your orbitals, you're going to increase the wavelength of light that's absorbed. And we'll talk much more about that in the next few videos, because that's where the idea of color comes in. On the right, we have the dot structure for beta.
Lambert-Beal law. Okay, there is one. UV spectroscopy, conjugation. Do we have colors? Determining structures by spectrometry.
Which is an orange molecule that's responsible for the color of carrots. On the left is the absorption spectrum for beta carotene. And the reason why beta carotene has a color is because it absorbs light in the visible region of the electromagnetic spectrum. The visible region starts at approximately 400 nanometers. So if I draw a line right here, to the left of that line would be the ultraviolet, the UV region of the electromagnetic spectrum, and on the right would be the visible region. So we see that beta carotene absorbs light, right, with wavelengths of approximately 450 to 500 nanometers for a range, and it absorbs strongly in the visible region. To explain why beta carotene is orange, we need to look in a little bit more detail at the visible region of the electromagnetic spectrum. And so here we have the different colors, right, the colors in the visible region, so essentially the colors of the rainbow. Approximately 400 nanometers, we're talking about violet light, right? So we have violet light right here. If you go beyond violet light, you're in the ultraviolet region or the UV region. So the visible region goes to somewhere around 700 nanometers or a little bit beyond that. So when you're in 700 nanometers, you're talking about red light. And if you go just past red light, you are in the infrared region of the electromagnetic spectrum. And here I have 6 colors. I have red, orange, yellow, green, blue, and violet. And when Isaac Newton did his famous experiment with a prism, and he wrote down 7 colors. So he included indigo because he wanted to have 7 colors in the visible region. So you usually memorize Roy G. Biv for the colors of the rainbow. But the reason I've left out indigo here is because this allows us to better see a color wheel. So Isaac Newton was the first to represent a color wheel, right? And you get a color wheel by taking the violet, right, and moving it over here, and taking the red and moving it over here. And so you put the violet right next to the red, and so you get a color wheel. It's useful to look at a color wheel because it allows you to see the relationship between complementary colors. For example, if I wanted to know the complementary color for red, all I have to do is look across on my color wheel, and I can see that the complementary color is green. The complementary color for violet, if I look directly across, that would be yellow. And then finally, the complementary color for blue would be orange. And this is useful because it allows you to think about why things appear to be a certain color. For example, if I look at this orange sheet of paper here, and we try to understand why this sheet of paper is orange, we know that white light consists of all of these different wavelengths, right? We know white light consists of all of the different colors of the rainbow here. We can simplify that even further, and we can think about white light being 2 complementary colors. So we could say, oh, okay, so this part consists of blue wavelengths of light, and then on the right here, this part of the color wheel consists of orange wavelengths of light. And we could think about white light consisting of blue wavelengths and orange wavelengths. So if we have white light coming in, here are the blue wavelengths of light, and then we have the orange wavelengths of light. So this is an oversimplified way to think about white light striking our orange object here. So if the object absorbs the blue wavelengths of light, right? So we're absorbing the blue wavelengths of light. Therefore, we are reflecting the orange wavelengths. And so if we reflect the orange wavelengths of light, and our eye happens to be right here, so we see the object as being orange. So our brains perceive the object as being orange because we are seeing the reflected orange light. And so that's how to think about why something appears to be a certain color. If I go back up here to beta carotene again, right? So I look and see where beta carotene is absorbing. Beta carotene is absorbing somewhere in the range of 450 to 500 nanometers, and those are blue wavelengths of light, right? If I look at it down here, so 450 to 500 nanometers, right? We're absorbing the blue wavelengths of light. Therefore, we are reflecting the orange wavelengths. And so we perceive beta carotene to be orange. And so that's a little bit of the theory behind why we perceive something as having a certain color. In the next video, we're going to talk about how this dot structure of beta carotene allows the molecule to be colored.
Okay.
Most organic molecules don't have any color at all. An example of that would be ethene or ethylene. So ethene has 2 carbons, and each of those carbons is sp2 hybridized. So each of those carbons has a p orbital. So we have a total of 2 p orbitals, or 2 atomic orbitals, and those 2 atomic orbitals are going to recombine to form 2 molecular orbitals. Different molecules can absorb different wavelengths of light, and if a molecule happens to absorb light in the ultraviolet or the visible region of the electromagnetic spectrum, we can find the wavelength or wavelengths of light that are absorbed by that compound by using a UV-vis spectrophotometer. And essentially what that does is it shines light with a range of wavelengths. So the wavelengths range from approximately 200 nanometers all the way up to 800 nanometers.
I'm sorry, I'm sure it's in here somewhere.
Let's talk spectrophotometry.
He knows a lot about the science stuff. Professor Dave explains.
As we have learned in a previous tutorial, kinetics is the study of reaction rates. Sometimes we will want to know how quickly or slowly a chemical reaction will happen. Therefore, any kinetic study will require monitoring the concentrations of a particular reactant or product over time to see how quickly they are being used up or formed. Of course, we can't see molecules and count them. They are just too small and too many. So to do this, we have to be clever. We can measure the mass of a precipitate as it is forming, or we can measure the volume or even the pressure of a gas that is produced over time. But what if a reaction does not produce a product in a different phase than the solution? Luckily, one of the most reliable methods involves using spectroscopy, which is the study of how light interacts with matter. So let's learn about this technique now. All molecules absorb and emit light differently based on what kinds of covalent bonds are in the molecule. If the products and reactants interact with light differently enough that there is a color change as the reaction occurs, we can monitor this process with an instrument called a spectrophotometer in order to measure changing concentrations. This will give us data in the form of an absorption spectrum, which displays how much light through a band of frequencies is able to pass through a sample to reach the detector. Where there are peaks, it means that not as much of the light of that wavelength is getting to the detector, which means that it is being absorbed by the sample. If we collect data like this continuously over the duration of a chemical reaction, we can gather information about how rapidly the absorbance changes, and thus how the concentration of a particular substance is changing over time. In order to do this, we will use an equation that relates the amount of material in a sample to the absorption of light passing through it, and this is called Beer's law. Here, A is for absorbance. This symbol represents something called the molar absorptivity, a measure of how well a chemical species absorbs a given wavelength of light. B represents the path length, or the distance light has to travel through the sample, which is relevant because the more of a substance the light travels through, the more of it that will be absorbed. And C is the concentration of the sample, which again is relevant because the more concentrated, the more absorbance that will occur. Absorbance is measured by comparing the intensity of the beam of light as it enters the sample and the intensity as it leaves the sample and strikes the detector, which are I0 and I respectively. And A will be equal to the log of I0 over I, or equivalently, the negative log of I over I0. If we plug the latter version into the original equation, substituting for A, and then solve for I, we can get this version of the law, which displays the exponential relationship between variables that are easily measurable. The primary advantage of this technique is that we can just let a reaction occur normally and measure the rate indirectly by analyzing the light that interacts with the components in solution, rather than stopping the reaction and measuring concentrations directly. Let's try one calculation to put this into context. Say that a substance has a molar absorptivity of 0.35 inverse centimeters inverse molarity. Light passes through a 2 centimeter sample and hits the detector with an intensity of 0.12 compared with the incident beam. What is the concentration of the sample? If we want to use the more basic version of Beer's law, then first we need to calculate the absorption. We can use this simple equation from before, plugging in 1 for the initial intensity and 0.12 for the other intensity. That gives us 0.9208 for A. Then we will use Beer's law. We can rearrange to solve for C, our unknown, plug in the absorption we calculated, plus the two given values, and we should get around 1.3 molar for the concentration of the analyte. Gathering this kind of information regarding concentration and plotting it in real time using computer software will allow us to easily infer all kinds of things about the rate law and hence the reaction mechanism for the reaction that is happening in solution, which is incredibly useful data. To get just a bit more practice, let's check comprehension.
Wait, a compound has a molar absorptivity 40.9 per centimeter per molar at 298 nanometers. If a 1 centimeter curvet is used and absorbance is found to be 0.111, what is the concentration of the sample? Okay, molar absorptivity, that should be the epsilon symbol. What's the Beer-Lambert's law? Epsilon. Okay, so I think that's the thickness. No, this would be the thickness. So what is the nanometer? Yep. So absorbance, okay. 40.9, that was epsilon times B. What is B? What is oh fuck. Okay, that's thickness, okay. Okay.
Content. And as always, feel free to
Yeah, this was the one I was looking for.
Auf Vinted wird alles wieder neu.
Over spectrophotometry and cover some problems on Beer-Lambert's law. So let's start with this one. The intensity of the incident light on a sample is 0.5 watts per square meter, and the intensity of light entering the detector is 0.36 watts per square meter. Calculate the transmittance and determine the absorbance. So let's draw a picture. So first we have some sort of light source. Let me draw a better light bulb. So it emits all types of light with different wavelengths. And so that light passes through a monochromator, which could be basically a prism or grating. And this device selects a wavelength. And so the amount of light that leaves the prism or the grating and that passes through the sample, that's known as the incident intensity. Now the sample is going to absorb some of that visible radiation, and some of it is going to pass through.
Okay, I understand those.
Through and hits the detector is simply I. Now the transmittance is the ratio between I and I0. So the intensity of light entering the detector, I, is 0.36. The incident light, I0, is 0.5. So 0.36 divided by 0.50, that's 0.72. So that is the transmittance of the solution. Now, what does this number mean in terms of practical numbers? So let's draw the sample again. And let's say the incident intensity is 100%. only 72% will pass through the solution and go through the detector. And that's the transmittance, how much actually passes through the sample. So the other 28% was actually absorbed by the molecules in the sample. So now that you understand the basic concept of transmittance, let's calculate the absorbance. So the absorbance is equal to negative log of the transmittance, or you could say negative log of I over IO. Now we know the transmittance, it's 0.72. So if we take a negative log of 0.72, that's going to equal positive 0.1427. And so that is the absorbance of the sample. So as the transmittance increases, the absorbance decreases. The transmittance is between 0 and 1. It can't be more than 1. You can't have more than 100% passing through the sample. So let's talk about the relationship between these two. So let's say if this is 1, 0.5, 0.1, 0.01, and 0.001. So the absorbance, we know it's a negative log of the transmittance. So if you type in negative log of 1, you will get 0. So this is the highest that the transmittance could be, because the lowest that the absorbance could be is 0. So at 100% transmittance, there is no absorbance. Now let's say if the transmittance is 50%. So negative log of 0.5, that means that the absorbance is 0.301. Now at 0.1, negative log of 0.1 is 1. So if it's 10% transmittance, then the absorbance is 1. Negative log of 0.01 is 2. This is, by the way, 10 to the minus 2. And this is 10 to negative 3, so the absorbance will be 3. So as the transmittance decreases, the absorbance will increase. And the maximum transmittance is 1, which means the minimum absorbance can be 0. So hopefully this table gives you a good understanding between the relationship of transmittance and absorbance. Number 2, a 0.25 molar solution in a test tube with a path length of 1 centimeter has an absorbance of 0.075 at 560 nanometers. What is the molar absorptivity of the solution? So according to Beer-Lambert's law, the absorbance is equal to the molar absorptivity times the path length times the concentration of the solution. So we're given the absorbance, that's 0.075. And our goal is to calculate the molar absorptivity. The path length is 1 centimeter, and the concentration is 0.25 moles per liter, or you could just say capital M. So then the molar absorptivity is
Wait. I still got a chance for physics. Okay. And then there's introductory lab course and exercises in chemical calculation. Okay. If I get physics, that's good. That's really good. Let's do up. Introductions to biological chemistry. What kind of
half-length times the concentration of the solution. So we're given the absorbance, that's 0.075. And our goal is to calculate the molar absorptivity. The path length is 1 centimeter, and the concentration is 0.25 moles per liter, or you could just say capital M. So then the molar absorptivity is going to be 0.075 divided by 0.25. The 1 is not going to change anything.
Yep.
So it's going to be 0.3, and the units is liters divided by moles per centimeter. Or you could say it's 0.3 m to the negative 1 cm to the minus 1. So this is the molar absorptivity. Part B. What will be the absorbance if the concentration of the solution is 0.65 moles per liter? So now that we have the molar absorptivity, we can calculate the absorbance. So the molar absorptivity is 0.3. The path length is still 1 centimeter. And the
0.65,
concentration is
okay.
now 0.65 moles per liter. So if you want to see how the units work out, let me write it out. So the molar absorptivity have the units liters per mole per centimeter. And the path length is 1 centimeter. The concentration is 0.65 moles per liter. So you can see that the unit liters will cancel, centimeters will cancel,
Mole will
and moles
cancel.
will cancel. So absorbance is unitless. So it's just going to be 0.3 times 1 times 0.65. So in this example, the absorbance is 0.195. So that's the answer for part B. Now part C, what is the concentration if the absorbance is 0.45? So let's replace A with 0.45. The molar absorptivity is 0.3. L is still 1. Now let's calculate C. So it's going to be 0.45 divided by 0.3. So the concentration is going to be 1.5 moles per liter. So we have a 1.5 molar solution. And so that's it. So if you have the molar absorptivity, you can easily calculate the absorbance or the concentration of the solution. Number 3. The table below shows the relationship between the absorbance of a solution and its concentration given a path length of 1 centimeter. Write a linear equation that fits the data to a reasonable degree. So if you were to make a plot between the absorbance and the concentration, you should get a straight line graph that looks like this. So therefore, we can write a linear equation to describe the data. Now you could use the least squares method, which is more accurate. You can use. The table below shows the relationship between the absorbance. So if you were to make a plot between the absorbance and the concentration, you should get a straight line graph that looks like this. So therefore, we can write a linear equation to describe the data. Now you could use the least squares method, which is more accurate. You can use Excel as well. But I'm going to use a simple method of picking 2 points and writing the equation of the line between those 2 points. So first we need to calculate the slope, which is the difference between the y values divided by the difference of the x values. So let's choose x for concentration and y for absorbance. So we could say that it's technically A2 minus A1 over C2 minus C1. So I'm going to choose this as A1 and the last one as A2. So this is going to be C1 and C2. So A2 is going to be 0.682. A1 is going to be 0.072. And then C2 is 1.421. And C1 is 0.150. So the change in the absorbance, using the first and last points, is 0.61. And the change in concentration is 1.271. So if we divide these two numbers, the slope is 0.48. So the last thing we need to calculate is the y-intercept. So let's use the slope-intercept form of a linear equation. And we can choose any point. I'm going to use the first point, where x is 0.15 and y is 0.072. So I'm going to replace y, the absorbance, with 0.072. M is 0.48, and x is 0.15. Let's calculate b, the y-intercept. So 0.45 times 0.15, intercept form of a linear equation. And we can choose any point. I'm going to use the first point, where x is 0.15 and y is 0.072. So I'm going to replace y, the absorbance, with 0.072. M is 0.48, and x is 0.15. Let's calculate b, the y-intercept. So 0.45 times 0.15, it's 0.48 times 0.15. That's 0.072. So if we subtract both sides by 0.072, we can see that b is 0. So therefore, the linear equation is as follows. All we need to do is replace m and b. So it's going to be y is equal to 0.48 times x, and b is 0. So this is the linear equation that describes it. Now a is y, and c is x. So we could say that a is equal to 0.48 times c. So now that we have the relationship between a and c, we can answer every other question. What is the absorbance when the concentration is 0.482?
Plug it into the equation.
So all you got to do is replace c with 0.482. So 0.48 times 0.482, that's going to be 0.231 if you round it. Now, does this answer make sense? So if the concentration is between these two values, 0.482 is between 0.351 and 0.617. Therefore, the absorbance should be between these two values, 0.168 and 0.296, which it is. So that answer does make sense. Now let's move on to part C. What is the concentration if the absorbance is 0.521? Now 0.521 is between these two numbers. It's between 0.458 and 0.682. Therefore, the concentration, we should expect it to be between 0.955 and 1.421. So let's go ahead and get the answer. So let's replace A with 0.521. And let's calculate C. So it's going to be 0.521 divided by 0.48. And so the concentration is 1.085, which is between 0.955 and 1.421. And so this answer is reasonable as well. So that's a simple way in which you can calculate the absorbance and concentration if you're given a data table. Now, if the path length is 1 centimeter, what is the molar absorptivity of the solution? So recall that A is equal to the molar absorptivity times L times C. So A is the same and C is the same in that equation. Therefore, we should expect that 0.48 has to equal this. Now, C is in molarity, moles per liter, and L is in centimeters. So therefore, the molar absorptivity has to be in liters per mole per centimeter. Now we're given the path length, which is 1 centimeter. And we could set 0.48 equal to epsilon times L. So if the path length is 1, then we can see that the molar absorptivity is going to be 0.48 liters per mole per centimeter. So that's how you can calculate the molar absorptivity given the data table. Now, is there an easier way to get these two answers without
Damn, that
writing a
took
linear
that long.
equation? Just by using this table directly, can we get these two answers? And it turns out that there is a simpler way to do this problem. Now, this is of course if your data fits a nice line. If it's not linear, then this technique may not be the best thing. You may have to find the best fit line using the least squares method or using Excel. So let's go back to this problem. The formula that you want to use is this equation. A2 divided by A1 is equal to M2 divided by M1, or C2 over C1. The concentration and the absorbance are proportional. Now, A1, you could use any one of these points, but I'm going to choose A1 as the first one, 0.072. And C1 is going to be 0.15, so that's not going to change. Now, in part B, I want to calculate the absorbance when the concentration is 0.482. So C2 is going to be 0.482, and I need to calculate A2. So it's going to be A2 over A1, which is 0.072, and that's equals to C2, which is 0.482, divided by C1, which is 0.15. So what we need to do is cross multiply. 0.072 times 0.482, that's 0.034704. And that's equal to 0.15 times A2. So now we need to divide both sides by 0.15. So A2 is going to be 0.034704 divided by 0.15. And that's going to be 0.231. So we get the same answer. Now, let's move on to the last part, part C. So this time, we're given the absorbance A2, and we wish to calculate the concentration C2. So A2 is 0.521, A1 is 0.072, and then C1 is 0.15. So once again, cross multiply. 0.521 times 0.15, that's 0.07815. And that's equal to 0.072 C2. Now, 0.07815 divided by 0.072, that's equal to 1.085. And so that will give us this concentration. So you have multiple ways in which you can solve these types of problems. So that's all I got for this video. Thanks for watching, and have a good day.
So, Beer-Lambert's law. There's going to be two different intensity between when light passes through the required substance or compound, and we could calculate absorbance of light using the formula A equals lambda times C times L, where C is the concentration, L is the thickness, and the lambda is the molar absorptivity. Beep 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 beep. Okay, I think it's time for me to use GPT. I still don't know how close I am with the question paper. That's the problem. I need to make sure I use the time. What is this even? Is that a triple bond? I guess that's a triple bond, yeah. To which class does the compound belong? Infrared spectrum A. Where is A? It's B. An unknown compound. Okay, as a formula C7H H12O2 and infrared spectrum A. To which class does this compound belong? I don't know. Use the other spectra NMRB and FIRDE and F and spectroscopic and chemical information in the reaction sequence to determine the structure of compound A and other unknown substance B through F. Okay, that's for A. For B, okay. Now I'm getting something. That's for AB. There's no C. A B C D F G H D A B C D E. Where's C? There's no C. What the hell? There's no C. There's no C. Open chain Fisher project structures for L-ribose and L-glucose. What are their systematic names? Please describe the term muto-rotation using one of the two carbohydrates. Please describe the reaction mechanism in detail. Of the following chemical conversion. So it's an alcohol. It's an alcohol. This one is phenol. Phenolic acid. And PH3P. Give mechanism for these reactions, explaining the selectivity or the lack of it in each case. I don't know what these stuff are. Explain the various pKa values for their derivatives of the naturally occurring amino acid, glutamic acid. Say which pKa belongs to which functional groups and explain why they vary in different derivatives. pKa values for the amino acid cysteine are 1.8, 8.3, 10.8. Assign these pKa values to the functional groups in cysteine and draw the structure of molecule in aqueous solution at the following pH. God damn. Well, no. Now let's go for the first question, Ray. Again, could you answer all the questions as I'm having my exam? The questions with explanations as I gotta do my chemical calculation homework. Oh shit. I gotta do those. You know what, people? I'm gonna take a 15-minute break. Or 13. Maybe serious set a timer for 13 minutes.
13 minutes. Counting
It's
down.
not even visible. What the? 13 minutes. Be right back. Well, YouTube, we back. We're back. I think I should stop. I should first send the first video, then I use the second video. Oh, dude, I'm hungry, kinda hungry, bro. Which we could get. Okay, so what did I type? Excessive shit. Exercise. Talking about exercise, I did not exercise today. Name the substance and assign RS configuration. So let's look at the RS configuration. I do remember it, but do you know there's no harm in looking it up again. There ain't no harm in it.
Timeless?
No, this shit ain't timeless, bro. It's Adidas. It's Adibas. It's Adi do.
For this particular model.
Imagine being able to build
Imagine just don't existing, okay? Imagine yourself not existing in front of me. Could you imagine that?
To chiral centers, including Fisher projections, and
I tell you, bro, this I ain't playing, bro. I ain't playing. Gotta tell you that. I ain't fucking playing, bro. This shit's serious, bro. Imagine that. Shut the fuck up, bitch ass Nick. Ho. I'm sorry, I just looked at my video. I actually accidentally opened my stream and I just heard my noise. I just heard me talking. That's who I said shut the fuck up. Not to this person who made this video. I said shut the fuck up to myself. And I have all the goddamn right in the world to say that. Ain't nobody gonna take it away from me.
Examples as well. So let's start with this one. Assign a R or S configuration to each chiral center.
Okay, let's just write everything we see in front of the screen. You know what? Instead of just sitting there and I understand. I understand. Just write, bro. Just write. Just write what you see, bro. Just do it, bro. Let's just erase the mass spectrometry and let's just write about RS configuration. Stereochemistry. Stereochemistry. RS configuration and Fisher projection. Yeah, those are both I need.
In this video, we're going to talk about stereo.
I gotta write this question. And we got the chlorine, hydrogen, metal, chlorine, bromine. Oh, and another where chlorine is attached, metal is on the top, and hydrogen. Oh, bromine.
We're going to talk about how to assign RS configuration to chiral centers, including Fisher projections, and a lot of other examples as well. So let's start with this one. Assign a R or S configuration to each chiral center shown below. So first, what is a chiral center?
It's the
chiral
center of the
center,
chiral, you know what I'm saying? It's the central carbon atom attached to 4 different functional groups or what's the word? 4 functional groups or halogen, anything.
A chiral carbon is a carbon atom that has 4 different groups attached to it.
Just
in this
different
case,
groups.
These are the 4 different groups. Now, in order to assign that chiral center a RS configuration, we need to rank those 4 groups using the Kahn-Engel prelog process.
What? What process?
Using the Kahn-Engel prelog process.
Kahn-Engel prelog process, okay.
Group number 1 is going to have the highest priority. And the way we determine priority is based on atomic number. So looking at these 4 atoms, bromine, chlorine, carbon, and hydrogen, which of these 4 atoms have the highest atomic number based on the periodic table?
Bromine.
So if you're using the periodic table, you'll find that bromine has the highest atomic number.
Oh yeah.
So this is going to be group number 1. It has the highest priority. Chlorine has the second highest atomic number relative to bromine. So that's going to be group number 2.
Metal.
Carbon has an atomic number of 12.
Oh, just the carbon?
Hydrogen has the lowest atomic number of all of the elements in the periodic table. It has an atomic number of 1. So it's always going to be group number 4. Now, before we can count it, we need to make sure group number 4 is in the back, or it's in the hatch wedge, which it is in this case. So we can count it from 1 to 2 to 3. So notice that we're rotating in the counterclockwise direction. Whenever that happens, you need to assign an S configuration if group number 4 is in the back. So that's the configuration for this particular chiral center. Now let's focus on the chiral center on the right. And if you want to pause the video to try that example, feel free to do so.
I mean, I know
This
it's
bromine atom, we know it's going to be
the
number 1.
R.
Chlorine is going to be 2. The methyl group will be group number 3, and H is 4. So counting it from 1 to 2 to 3, this time we are rotating in the clockwise direction. So this is going to have the R configuration. Now looking at these 2 molecules, what is the relationship between them? Would you describe them as constitutional isomers, enantiomers, diastereomers, meso compounds? How
Mirror.
would you describe these 2 compounds?
Mirror.
Now notice that these 2 molecules are mirror images of each other. Therefore,
Mirror images.
they are known as enantiomers.
I didn't know that.
Enantiomers are a special type of stereoisomer. A stereoisomer, like any other isomer, have the same chemical formula.
Wait.
They're connected the
When
same.
I press enter, you gotta pause. Yeah. Mirror images of same compound. Therefore, enantiomers. What?
Like any other isomer. Special type. They are known as enantiomers.
Enantiomers.
Enantiomers are a special type of stereoisomer. A stereoisomer, like any other isomer, have the same chemical formula. They're connected the same way. But notice that the way the atoms are arranged in space, it's arranged in space differently. This carbon and that carbon, they're connected to the same 4 groups. But the way those 4 groups are arranged in space, they're not the same. Here, chlorine is on the left side. Here, it's on the right side. So they are arranged in space differently, which makes it a certain type of stereoisomer. Diastereomers, enantiomers, cis-trans geometric isomers, those are all stereoisomers. But enantiomers, they're mirror images of each other. And that's how you can distinguish them from diastereomers. Another feature of enantiomers is that they have the opposite configuration at the chiral center. Here, the configuration, we determine it to be S. Here, it's R. Now, let's work on some more examples for the sake of practice.
For the sake of practice.
So go ahead and assign the R and S configuration to each chiral center that I'm going to draw. So let's put an ethyl group here. Let's add a hydrogen, a bromine atom, and let's put a hydroxyl group. So go ahead and determine the configuration at this carbon. And so while you do that, I'm going to write up another one.
I wanted to surprise my father with something really delicious to eat on our Father.
Okay, let me draw both of these. They're not complete.
So let's start with the first one. The first thing we need to do is determine which group has the highest priority. So we know it's going to be bromine.
Oh yeah, it's bromine. 2 carbon. Or oxygen.
Next, if we compare oxygen to carbon and hydrogen, we know oxygen is going to have a higher atomic number. The atomic number for oxygen is 8, for carbon is 6. So this is going to be number 2, 3, and then hydrogen is always 4. Now hydrogen is in the back, which is good. So we're going to just go from 1 to 2 to 3. And so for this one, we have the R configuration. We're rotating clockwise, or in the direction of a clock. Now for the next one, hydrogen is going to be group number 4. Here we have oxygen, carbon, carbon. Oxygen wins, so that's going to be number 1.
Boy. Yeah, oxygen, then the carbon, 2 carbon, then the 3 carbon, then the normal carbon and hydrogen. Yeah. But the metal group, the hydrogen is above the carbon. So we usually write it like this, but we change. Yeah, this one looks like an R configuration. But no, it's an S. Configuration when the hydrogen is below. This is a real R configuration.
Next, notice that these two carbons, they have the same top number. So if we move on to the next group, here we have carbon versus hydrogen, carbon wins. So the ethyl group has a higher priority than the methyl group. So if we count it from 1 to 2 to 3, notice that we're rotating in the clockwise direction, but group number 4, it's not in the back, it's in the front. It's not on the dash, this time it's on the solid wedge.
Yep.
So because it's on the solid wedge, or it's in the front, coming out of the paper, we need to rotate it. So just switch the configuration, and it's equivalent to putting it back to putting group number 4 in the back. So it was R, but now it's S. So that's the configuration for this chiral center. So anytime H is in the front, simply count it from 1, 2 to 3, and then reverse your answer. Number 2, name the following compounds using the RS system for stereoisomers. So first, let's identify the chiral center. So let's focus on this carbon. That carbon has a bromine, a hydrogen, a methyl group, and an ethyl group. So it has 4 different groups, which makes it a chiral center. Now let's rank those groups. Bromine has the highest atomic number, that's going to be number 1. We know ethyl has a higher priority than methyl. So this will be 2, that's going to be 3, H is going to be 4. So going from 1 to 2 to 3.
No, we got the next one. Well, let's do the next one. Now we got a hydrogen on the top and bromine on the bottom.
You see that it's going in the R direction. And when you count from 1 to 2 to 3, ignore 4. Now after you count it, we're going to focus on 4. 4 is in the front, it's not in the back, which means we need to reverse it. So it's going counterclockwise, which means the configuration is S.
Now the next one. We got chlorine at the top, hydrogen at the bottom, but on the other side it's hydrogen at the top, bromine at the bottom. So it's gonna be
For
interesting.
the S configuration here. Now, in order to name it, we need to count the carbons in the parent chain. So we're going to count it in this direction. So we have a 4-carbon parent chain. We're going to be dealing with butane. So first, we need to write the configuration of the chiral center, which is S. We're going to enclose that in parentheses. And then it's going to be, we have a bromine on carbon 2, so 2 bromo.
Oh, we got a name.
And for 4-carbon alkane, that's going to be butane. So it's S2-bromo-butane. That's how we can name this particular stereoisomer. Now, let's move on to the next one. So here we have 2 chiral centers. And you could check it. Here we have 1 group, 2, 3. Relative to this carbon, this is the 4th group. if we focus on the second chiral center, this is one group, 2, the ethyl's 3, and that's the fourth group. So let's focus on the first chiral center, this one. So we're comparing a chlorine atom, hydrogen, carbon, carbon. So if we look at the first atom that's connected to that chiral center, we see that chlorine has the highest atomic number. We don't look at bromine because it's not the first atom attached to this chiral center. So we look at it from a 1-to-1 basis. So this chlorine has a higher atomic number than that carbon. So this is going to be group number 1. Now for group number 2, we know H is number 4. So we got to compare these two. Here we have a carbon, and then a carbon, and then after that carbon there's a hydrogen. Here there's a bromine. This is going to win. So this entire group is group number 3, which makes the methyl group.
Opposite.
Actually, take that back.
Yeah.
This is 2, this is number 3. This has a higher priority than the methyl group. So now we can count it from 1 to 2 to 3. And so that's going to be the R configuration.
I need to find the best way to learn math and science.
Oh no, I don't
It's
need to
brilliant,
find.
that
Get the fuck out of here, bro.
So let's put R here. And now let's focus on the next chiral center. So bromine, hydrogen, carbon, carbon. Bromine's going to have the highest atomic number. So that's 1. H will be 4. So now let's compare these two. So those two carbon atoms are the same. Next we have a chlorine versus a carbon. The chlorine's going to win. So this whole group will be group number 2. And the ethyl group is going to be number 3. So going from 1 to 2 to 3, we're going in the R direction, but H is in the front. We're going to have to reverse it, making it S.
Oh, the naming.
So this is S. Now that we've assigned the configuration to each chiral center, we can name this stereoisomer. So we need to number it from left to right. So the substituents will be on 2, 3, as opposed to 3, 4. Now, on carbon 2, we have the R configuration, so this is going to be 2R.
Well, what?
And on
It's going down. It's going clockwise. Clockwise is R. Okay, I confuse. What? Clockwise is R. S is anti. Okay. Okay.
3, we have the S configuration. So this is going to be 3S. Now we need a comma between them. And then we need to put the bromo and the chloro group in alphabetical order. So B comes before C.
3 bromo.
This is going to be 3 bromo.
2
It's on
chloro.
carbon 3. Chlorine's on carbon 2, so we're going to have 2 chloro. And for a 5 carbon alkane, that's going to be pentane. So this is 2R, 3S, 3 bromo, 2 chloropentane. So that's how we can name this particular stereoisomer. Now here's a question for you. How many stereoisomers are possible if you have 1 chiral center? And how many are possible if you have 2 chiral centers? So if you have 1 chiral center, you can have the S isomer or you can have the R isomer. So there's 2 possibilities. The equation that will give you the number of stereoisomers is 2 to the n, where n is the number of chiral centers. So in this case, n is 1, 2 to the first power is 2. So for one chiral center, there are 2 possible stereoisomers. Now what if we have 2 chiral centers?
It's 4.
How many stereoisomers are possible? Well, it's going to be n is 2, so it's going to be 2 squared. 2 squared is 2 times 2, which is 4. So we have 4 possibilities. The first possibility is if both chiral centers are R. The second one is if one is R, if the first one's R and the second one is S, or if the first one's S, the second one's R, or if they're both S. So those are the 4 possibilities, or the 4 stereoisomers that are possible if you have 2 chiral centers. So the number of stereoisomers is going to be 2 to the n chiral centers. Number 3, the chemical structure of cholesterol is shown below. How many stereoisomers are possible for this molecule? So feel free to take a minute and...
I'm gonna take a lot of minutes. First I gotta write these, gotta draw these. CH3. How many chiral centers? Yeah, 1. 2. 3. 4. 5. 6. I must say 6.
this problem. So this right here is a chiral center. We have an OH group.
Okay, I missed that. 7.
An invisible hydrogen, but now it's visible. And then this side is different than that side. This side is closer to the double bond. This other side has a methyl group. So these two sides are different, which makes this a chiral center. Now, this carbon is also a chiral center. It has 4 different groups. Here we have a methyl group. Here is a secondary carbon, a tertiary carbon, and this tertiary carbon. This tertiary carbon is close to the double bond. This one is not. So they're different, which makes this a chiral center.
The next one.
Here is another chiral center. This is one group, this is another, this one's another, and there is a hydrogen attached to it. And we could put that hydrogen here. This carbon here is not chiral. Whenever you see a carbon with 2 bonds and that's it, it's a CH2 carbon, which means it doesn't have 4 different groups because these are the same. So that is not a chiral carbon.
This one.
So it's best to focus on the tertiary carbons and the quaternary carbons. This is a tertiary carbon. It's attached to 3 other carbons, and there's a hydrogen attached to it. So that is another chiral center.
Okay, forgot about that.
Here's another tertiary carbon. It has 3 other carbons, all of which are different, and there's a hydrogen here too. Now, this carbon here is quaternary. It's attached to 4 different carbon atoms. So that's another chiral carbon.
I'm gonna say 9.
This tertiary carbon is chiral too. There's a hydrogen here. And this carbon is tertiary and it's chiral. This is group 1. This is another group. This is another group. And then the hydrogen is the 4th group. So let's put that hydrogen on the hatch wedge. Now this carbon here is tertiary, but it's not chiral because it doesn't have 4 different groups. These 2 methyl groups are the same. Thus, cholesterol has a total of 1, 2, 3, 4, 5, 6, 7, 8 chiral centers. So because cholesterol has 8 chiral centers, it's going to have 2 to the 8 stereoisomers. 2 to the 8 is 2 to the 4 times 2 to the 4. 4 plus 4 is 8. If you multiply 2 4 times, 2 times 2 is 4, times 2 is 8, times 2 is 16. You get 16 times 16, which is 256. So this is a number of stereoisomers that are possible for this particular molecule. Number 4.
Wait.
Determine the
Before we start with number 4, where my calculator at? It's not even here. Two. There's no to the power. What we got now? Okay, 2. Nine. 2. No, okay. 2. 512 stereoisomers. Stereoisomers are possible. Determine the absolute configuration. Of each chiral center and name Fisher projection shown below.
Configuration of each chiral center and name each Fisher projection. Below. When dealing with Fisher projections, it's easy to determine the chiral center. So we have two chiral centers, which means that we have 4 possible stereoisomers for this particular structure. Now, before we determine the absolute configuration of each chiral center, let's talk about Fisher projections. So let's say if we have this particular Fisher projection. Let's make this an ethyl group. And let's say this is hydrogen, this is OH. What we need to realize is that the groups on the horizontal part of the Fisher projection, they're in the front. So you can redraw the structure like this if you want. They're coming out of the page. And so they're on the solid wedge. These two groups, they're on the dash or the hatch wedge. So they're going into the page. You can view them as being in the back. So make sure you understand that. Now, hydrogen is typically on the side, which means that as group number...
So if I'm redrawing this, CH3, another bond to bromine. Okay. Bromine, then it's bonded to hydrogen. CH3. Hi Josh. Hello, Devote. Appreciate Devote to that for checking out the stream. Yes, I am still on doing this stereochemistry, and yeah, I think I'll be ending the stream within those.
You're going to have to reverse it when determining the configuration. So keep that in mind.
But wait, let me make sure I drew this all right. So how these? So it's like they're okay.
Anytime group number 4 is in the front, you need to reverse it. So let's begin by determining the configuration of this chiral center. The hydroxyl group is going to be group number 1. Oxygen beats these 2 carbon atoms. Now, comparing those 2 carbon atoms, they're the same, but here we have a bromine, here is a hydrogen, so this group has a higher priority than the methyl group. So this will be group number 2, the methyl will be 3, and then hydrogen is always 4, if it's there. So going from 1 to 2 to 3, we're going in a clockwise.
Oxygen. Two. Yep, this would be 2. That would be 3, and this would be 4. So it's gonna go like this. Okay. So it's clockwise R configuration.
So that's R, but H, remember H, when it's in the horizontal part, it's like being on the solid wedge. H is in the front, so we gotta reverse it. So we're gonna get S. So we have the S configuration for that chiral center. Now for the next one, so we're gonna focus on this chiral center. Bromine is going to be group number 1. It has the highest priority. Next, we're comparing the methyl group with this group. So we have carbon to carbon, and then hydrogen to
That's
oxygen.
S.
Oxygen wins. So this entire group is going to be number 2. Methyl is 3, H is 4. So going from 1 to 2 to 3, it looks like we're going in the S direction, but if we reverse it, it's going to be R. So we have the R configuration here.
Yep. Get these ads out of here, bro. Come on.
So now that we've assigned the absolute configuration to each chiral center, we can go ahead and name this particular molecule. So the hydroxyl group is going to have priority over the bromine group. So we're going to count it in a way that we give the hydroxyl group the lower number. We want to give it a 2 instead of a 3. So we're going to count it in this direction.
Oh, that's a long chain. Okay.
So on carbon 2, we have the S configuration. So this is going to be 2S. And on carbon
BRH. One, 2, 3, 4. 2S, 3R. Oh, 2R.
3, we have the R configuration, so 3R.
Oh, yeah. Wait. Clockwise. Okay, 2S, yeah.
And then we have a bromine on carbon 3, so this is going to be 3-bromo, and the alcohol is going to be part of the parent name, and it's on carbon 2, so it's going to be 2-butanol because we have a 4-carbon chain.
2S, 3 bromo, 2-butanol. That's it. Wait. I'm gonna cut this, put it there. Yep. Two S, 3R. Three bromo. Two butanol.
So 2S, 3R, 3-bromo, 2-butanol. That's how we can name this particular Fischer projection. Now let's try another example. Go ahead and name this Fischer projection and determine the configuration at each chiral center, just like we did before.
Okay. That's the name. Determine the absolute configuration of each chiral center. Name each Fischer projection shown below. Now that's interesting because bromine and hydrogen are on the top. So I don't think there will be changes in configuration. We'll see.
So let's start with this one. Bromine is going to be group number 1. This group with the chlorine atom, we know that's going to be 2. Methyl is 3, H is 4. So going from 1 to 2 to 3, ignoring 4. This is going in the counterclockwise direction, so that's S. But H is in the front, so we need to reverse it.
But
so we're going to
bromine. Okay, nobody doesn't even care about bromine. Okay. One. No, that's chlorine. It's a chlorine. 2, that's 2. 3, 4. Yeah, that's clockwise. So R conf, which is S conf, H reversed. What do we name this? We take the parent chain to 2R 3S 2 bromo 3 chloro 2, 3, 4, 5 pentane. Let's see.
This one. Now for the second chiral center, chlorine is going to be group number 1. This entire group is number 2. If we compare carbon to carbon, it's a tie. And then carbon to bromine, bromine wins. So this is number 2. Ethyl is number 3. H is 4. So going from 1 to 2 to 3, skipping 4, it appears to be R, but H is in the front, so we reverse it, and we get the S configuration.
S configuration.
So now that we have the configuration at both chiral centers, we can name it. So we don't want to count in this direction, because this will be 3 and that will be 4. Rather, we want to count in this direction. So this will be 2 and this will be 3.
Yep.
So we have a 5 carbon chain, so we're dealing with pentane. But first, let's focus on the configuration. So the configuration is R at carbon 2, so we're going to have 2R. And then it's S at carbon 3, so 3S. And then we have a Br on carbon 2, and we need to put it in alphabetical order. B comes before C. So this is going to be 2 bromo, and then we have a Cl on carbon 3, so 3 chloro. And then for the 5 carbon chain, that's going to be pentane. So that's the nomenclature, or the IUPAC nomenclature for this particular Fischer projection. It's 2R, 3S, 2 bromo, 3 chloropentane. Now let's work on a more challenging problem. So let's say this chiral center has an ethyl group, a methyl group
Oh, what was
in
the
the front,
name?
And then we have a Cl on
2
carbon 3.
bromo, 3 chloro.
So 3 chloro.
Pentane.
And then for the 5 carbon chain, that's going to be pentane. Now let's work on a more challenging problem.
Okay.
So let's say this chiral center has an ethyl group, a methyl group in the front, and let's put a chlorine group in the back, and a hydrogen. Go ahead and assign the configuration to the chiral carbon. Is it R or S? Now this problem is different because hydrogen, group number 4, is neither in the front nor is it in the back. So how do you assign the configuration in this situation? Well, let's begin. We know that chlorine has the highest atomic number, so that's going to be group number 1. Ethyl has more priority than methyl. So ethyl is 2, methyl is 3, H is 4. In a situation like this, there's a technique that you could use to assign the configuration. Whatever group is in the back, put it in a circle. So I'm going to put 1 in the circle. And you could put a small subscript B to indicate that whatever in the circle is in the back. Sometimes it could be in the front, so. But for now, whatever's in the circle in this problem is in the back. Now, the other numbers, 2, 4, and 3, you want to arrange them in the form of a triangle. Now, if you notice, 2 is at the top, so let's put that at the top. 4 is at the bottom left with respect to 2, so let's put that here. 3 is on the bottom right. Now, what we're going to do is we're going to rotate this molecule in such a way that number 4 will be at the top where 2 is. So we're going to rotate it 120 degrees clockwise. So 1 is still in the circle. 4 has replaced 2. 2 is now where 3 was, and 3 is where 4 was. Now the next thing we're going to do is we're going to flip the molecule. As we flip it, 2 and 3 will move to the top. Group number 4 is going to expel group number 1. So now 4 is in a circle, 1 is beneath it, and then 3 and 2 are at the top. Now 4, group number 4 is in the back, because what's in a circle represents what's in the back. And so we can count it from 1 to 2 to 3, and this gives us the S isomer. So the configuration at this chiral center is S. So that's a technique that you could use whenever group number 4 is not in the front or in the back.
Wait. So. Think of it as a triangle. There's carbon at the center. The chlorine is at the bottom. Okay, now we shift in a way that Chlorine is at the top. Mm-hmm. We got 4. 4. Yeah. Mm-hmm. Yep. How do I think it when it's the exam? One. Mm-hmm. Now we got the configuration. So it's anti-clockwise, which is this configuration. I mean, we could just change it, but my greatest doubt would be how that'll be arranged. Yep. Let me see how it goes. This configuration. What's the name of the compound? Two S 2-chloro butane.
Now 4, group number 4 is in the back, because what's in a circle represents what's in the back. And so we can count it from 1 to 2 to 3, and this gives us the S isomer. So the configuration at this chiral center is S. So that's a technique that you could use whenever group number 4 is not in the front or in the back.
Oh, what was the last part? Oh,
use
you did.
Whenever group number 4 is not in the front or in the back.
Assign RRS configuration to each chiral center. In the Newman projection shown below. What the hell? I think it's 2 carbons between these two, or? Do we have a question like those? Not this one. Those are lecture notes. Oh yeah, maybe this one. No. Okay, oh, let me just write that question. Assign r/s configuration to each chiral center in the Newman projection shown below. We draw how this looks. 0. So 0, then we do Mercedes Benz, and then we do this. CH3 BR CH2OH HClH. Okay, that's a really amazing Newman's projection.
Right?
Okay, I thought I was right. What I had in mind, that was exactly how it is. Well, YouTube, I'm gonna end the stream. I gotta cook. I gotta eat something because human beings get hungry. That's a shame, but yeah, we do get hungry. So I gotta eat something and I gotta look into job hunt. Hell yeah. Peace out, YouTube.